So the next topic we're going to talk about is Laplace transform. Eventually we're going to use this Laplace transform to solve a differential equation. Right now we just need to get comfortable with what a Laplace transform is and how to evaluate it. So in calc, throughout your semesters of calc, we've learned about differentiation and integration and how those operations transform one function into another. And we've talked about that in relationship to differential operators, and then eventually annihilators. But ultimately, you can think of a derivative or an integral transforming one function into another. We also know that both of those operations have both the constant multiple and the sum and difference rule. And we talked about that being what's called the linearity property. Okay. So we're going to specifically focus on integration when it comes to Laplace transform. So if we're looking at a particular function, and we could say a two-variable function, so now you're thinking about some of your integration that we discussed in Calc 3, and you integrate a two-variable function with respect to one of the variables. Okay? Say, looking at this integral right here. We're going to integrate 2xy squared with respect to x. And then we're going to evaluate it between 1 and 2. But remember, 1 and 2, since we're integrating with respect to x, these are x values. Okay? So we're going to integrate this with respect to x, which we would get x squared, y squared. Then we're going to evaluate it between 1 and 2. So we'll plug 2 in for x, giving us 4y squared. Minus, we're going to plug 1 in for x, which gives us 1y squared. And we're going to get 3y squared. Okay? And sometimes we would then integrate with respect to y, but in this case, let's just look at it if we integrated with respect to one of the variables. And notice what just happened here. We used integration to turn one function into another. And not only that, we used integration to turn a function of two variables, x and y, into a function of one variable. And that variable was y. Because we integrated with respect to x, we're now left with a function of y. So in some instances, integration can turn one function into another, but more specifically, turn a function of two variables into a function of one variable. So if you were to look at, say, this integral right here, with these random functions, k and f. Overall, k is a function of s and t, and f is a function of t. So this whole thing right here is a function that has s's and t's in it. If we were to integrate it with respect to t and evaluate it between a and b, both being, again, t values, we would be left with a function of s. So this is just some basic stuff that we've discussed over the course of your time in calculus. The next thing we got to discuss is then the concept of an improper integral that we talked about way back in Calc 2. So when we're dealing with an improper integral, say something like this, where the limits of integration happen to be infinite on one or even both ends, we found a way to deal with that improper integral by removing the infinite limit of integration, replacing it with a b, and then doing the limit as b goes to infinity. So again, thinking about this whole thing here, we know that when we integrate a function of s and t with respect to t, we'll be left with a function of s in the long run. But even if the limit of integration happens to be infinite, we can still handle that by doing the limit as, say, that value goes to infinity. Something that we learned when we did these improper integrals is there's two options that can come out of an integral like this. Is one, the limit itself in the end could exist, in which case we say the integral is convergent. And then the limit could not exist, in which case we say that the integral is divergent. And if it's convergent, whatever we get out of this whole limit is the answer for the integral. And if it's divergent, it just diverges. Well, this specific integral has some meaning. There's a reason why we keep looking at this. This is essentially what we're going to define as a Laplace transform. And in this particular integral, this function k of s and t, we're going to call the kernel of the transform. Okay? And specifically for the Laplace transform, the kernel is going to be e to the negative st. So now for the definition of a Laplace transform. So let's look at a function here, f of t. And if we were to do the Laplace transform for f of t, we'll denote it with this cursive L of f of t. What we're basically going to do is we're going to plug this f of t into this integral, where it's the integral from 0 to infinity of e to the negative st times f of t dt. Now there's a possibility that this integral will not exist because the limit won't exist. But if the integral converges, then the answer we get out of it is what the Laplace transform for f of t would be. Okay? If the integral diverges, then the function f of t just does not have a Laplace transform. We'll use this notation down here, where if we apply the Laplace transform to a function f of t, we should get a function of s, and we'll use a capital F of s to denote it. So lowercase f for the function that goes into the Laplace transform, capital letter F for the function that comes out. A function of t goes in, a function of s comes out. So here would be another example. The Laplace transform of g of t equals capital G of s. So if we did it specifically with this example, let's do the Laplace transform of 1. So the Laplace transform of 1, we have to plug 1 in here for t, f of t. So we have the integral from 0 to infinity of e to the negative st times 1 dt. That's the integral we're going to have to do. So we'll do the limit as b goes to infinity of the integral from 0 to b of e to the negative st dt. We're going to integrate with respect to t, so that means we're going to hold s constant. So we have the limit as b goes to infinity of the integral with respect to t would be negative 1 over s e to the negative st between 0 and b. We would then get the limit as b goes to infinity of negative 1 over s. Plug in b for t and then plug in 0 for t. So I get e to the negative sb minus e to the 0. So that's going to again give me the limit as b goes to infinity of negative 1 over s. I can write this as 1 over e to the sb minus 1. As b goes to infinity, this thing's going to go to 0. So that'll just give me negative s times negative 1, so 1 over s. So the Laplace transform of 1 is 1 over s. Function of t turned into a function of s. Okay, now we can do the Laplace transform for t. So again, we're going to do the integral from 0 to infinity of e to the negative st times t dt. So that'll be the limit as b goes to infinity of the integral from 0 to b of e to the negative st t dt. So to do the integration, we're going to have to do by parts. U would be t, dv would be e to the negative st, du would be dt, and v would be negative 1 over s e to the negative st. So we would get the limit as b goes to infinity of negative 1 over s t e to the negative st minus the integral of v du, so that becomes plus 1 over s e to the negative st dt. This whole thing is going to have to be evaluated between 0 and b. So then we have the limit as b goes to infinity of negative 1 over s t e to the negative st This integral is going to give me negative 1 over s squared e to the negative st between 0 and b. I'll plug in b and I'll plug in 0. And you see we're going to get the limit as b goes to infinity. Negative 1 over s b e to the negative sb minus 1 over s squared e to the negative sb plus 1 over s 0 e to the 0 plus 1 over s squared e to the 0. Well, none of these have b's in them, so they're just going to be constants. This is the part that has b in it, so as b goes to infinity, what's going to happen? Well, remember, e to the negative sb, that's actually going to be in the denominator here, and same thing here. So as b goes to infinity, this thing's going to go to infinity, but it's in the denominator. This is also going to go to infinity. So if you use L'Hopital's rule, we could take the derivative of the top and bottom, but notice the denominator is going to grow much faster than the numerator will. So this whole fraction is going to go to 0. Same thing here, this thing's going to go to 0 as b goes to infinity. So ultimately the answer is just what we have here, but this is 0, so that's gone. So what do we get? 1 over s squared. So the Laplace transform of t is 1 over s squared. Let's do one more in this line of thought. So let's do the Laplace transform of t squared. So that would be the integral from 0 to infinity of e to the negative st t squared dt. So that'll be the limit as b goes to infinity of 0 to b, integral from 0 to b of e to the negative st t squared dt. If u equals t squared and dv equals e to the negative st, we'll do integration by parts. So 2t and v would be e to the negative st. We could also do the tabular method here if you wanted to do that too. We could say, all right, well, we got t squared, we got e to the negative st. So we have 2t, we have 2, we have 0. Here we're going to have negative 1 over s e to the negative st. Here we'll have positive 1 over s squared e to the negative st. Here we'll have negative 1 over s cubed e to the negative st. Then we'll match it. Plus, minus, plus. Either way, we're going to end up with this limit. The limit as b goes to infinity of negative 1 over s t squared e to the negative st. Then what? Negative 2t times 1 over s squared e to the negative st, and then negative 2 over s cubed e to the negative st between 0 and b. So you'll plug in b here, here, and here. You'll plug in 0. But as b goes to infinity, notice the same thing's going to happen. B is going to get plugged in for t, right? This is going to go to the denominator. As b goes to infinity, the denominator is going to grow faster than the numerator. That's going to go to 0. Same thing here. Same thing here. They're all going to go to 0 when we plug b in. So then what we're going to do is we're going to subtract out what happens when we plug in 0. Well, if we plug 0 in for t, that's going to be 0. That's going to be 0. And then we'll just be left with this one. So what do we get here? We get positive 2 over s cubed. Okay. So the Laplace transform of t squared is 2 over s cubed. So now take a look at this. Laplace transform of 1, which we could also say is the Laplace transform of t to the 0, was 1 over s. The Laplace transform of t to the first was 1 over s squared. The Laplace transform of t squared was 2 over s cubed. So then let's think, what's the Laplace transform of t cubed going to be? Well, I think you can clearly see the denominator is going to be s to the 4th. But what's the numerator going to be? Well, the numerator is actually going to be 6. Why? Because that's 3 factorial. The numerators here are matching up to be factorials because of what's happening here when we do integration by parts multiple times. Like let's say this was a t cubed instead of a t squared. Well, we would have t cubed, 3t squared, 6t, 6. The last one would be a 6, which is what we're going to end up with here. So if you think this is 0 factorial, this is 1 factorial, this is 2 factorial, so 3 factorial. So you see there's a pattern to these. So now if I asked you what's the Laplace transform of t to the 10th, rather than doing all this, you might be able to just tell me what the answer is by recognizing this pattern. And that's ultimately where we want to get. All right, how about the Laplace transform of e to the negative 3t? Totally different type of function. Now we're looking at an exponential function. So if we use the definition of Laplace transform, it should be the integral from 0 to infinity of e to the negative st times e to the negative 3t dt. Well, I can write this as the limit as b goes to infinity of the integral from 0 to b of e to the, I can write this a couple of ways. I'm going to be able to add these exponents together because these are multiplied bases and they're the same. I'm also going to factor out a negative. So I'm going to look at this as negative s plus 3t dt. So now when it comes to integrate, it's not that bad. We don't need by parts to integrate this thing. I'm going to have 1 over negative s plus 3 e to the negative s plus 3 t between 0 and b. So if I plug in my b, I have the limit as b goes to infinity of negative 1 over s plus 3 e to the negative s plus 3b minus e to the negative s plus 3 times 0. As b goes to infinity, again, negative exponent, this is actually in the denominator, that's going to go to 0. So then all I'm going to have is this times this, and this is really e to the 0, which is 1. So what do I end up with? 1 over s plus 3. So the Laplace transform of e to the negative 3t ends up being 1 over s plus 3. So then we can think about, okay, what would the Laplace transform of, say, e to the alpha t look like? Well, alpha is the negative 3, and kind of thinking about what was happening here, we could say maybe 1 over s minus alpha. That's bad alpha. Again, looking at a pattern to what would happen. If I just change the negative 3 to, I don't know, say a negative 5 or a negative 10 or positive 7, what would happen? Well, we'll just change what was happening here, and that's what's going to multiply into this. So again, seeing a pattern to what would happen here, if I change this Laplace transform, I don't necessarily have to do all this all the time. I could see what the answer might be right away. How about a trigonometric function? Now this one's going to be a little bit trickier, okay? But we can still get it done. It's the integral from 0 to infinity of e to the negative st times sine of 2t dt, which will be the limit as b goes to infinity of the integral from 0 to b of e to the negative st sine of 2t dt. We're going to need integration by parts to get this done. So u will be sine of 2t. dv will be negative 1 or e to the negative st. du would be 2 cosine 2t dt. And v would be negative 1 over s e to the negative st. And so we end up getting the limit as b goes to infinity of negative 1 over s e to the negative st times sine of 2t minus the integral of v du, so that becomes plus the integral of 2 over s e to the negative st cosine 2t dt. Okay, now to do that integral, we're going to need integration by parts again. U will be cosine 2t. dv will be 2 over s e to the negative st dt. du would be minus 2 sine 2t. V is going to be negative 2 over s squared e to the negative st. And so I'm now building up to the limit as b goes to infinity of negative 1 over s e to the negative st sine 2t minus 2 over s squared e to the negative st cosine 2t minus the integral of v du, so that'll be the integral of 4 over s squared sine 2t e to the negative st dt. Well, notice this is the same as the original integral again. This is one of those integration by parts where the original integral comes back up again. So what did we do when we had that? Well, what we did is we would move that over to the other side of the equation where this thing was, because remember, this is what it's equal to. We would basically add this coefficient onto it. Then we would flip and divide. To see this easier, you could just look at the integrals themselves. On this side, we have the integral of e to the negative st sine 2t dt. On the other side, we have all this. Okay? So if I add this to the other side of the equation, right, I have a 1 in front of here. I'm adding 4 over s squared to that. So what I now have is 1 plus 4 over s squared times the integral of e to the negative st sine 2t dt. Well, what is this really? This is going to be s squared plus 4 over s squared. Okay? And this is going to equal really what's left, which is just this piece here. So this negative 1 over s e to the negative st sine 2t minus 2 over s squared e to the negative st cosine 2t. So really we don't want to know what this whole thing equals, we just want to know what this equals. So now we're going to move this to the other side, so we're going to divide it, which means we're going to flip and multiply. So in the end, the final answer is going to be the limit as b goes to infinity of s squared over s squared plus 4 times negative 1 over s e to the negative st sine 2t minus 2 over s squared e to the negative st cosine 2t, and then that's going to have to be evaluated between 0 and b. Alright, so again, that was just one of those longer integration by parts where the original integral pops back up again. So now we're going to plug in b for t here and here and here. As b goes to infinity, remember this is again in the denominator. If we plug in b for this, remember sines and cosines always range between negative 1 and positive 1. But the denominator is going to go to infinity. Well, if that's going to be the case, this whole thing is going to go to 0. This is going to go to 0 when I plug in b. When I plug in 0 here and here for t, I'm going to get e to the 0, which is 1, times sine of 0, which is 0, so that's going to go to 0. I'll plug 0 in here and here. Cosine of 0 would be 1, and then I'd have e to the 0, which would be 1. So really I'm just going to get this negative 2 over s squared times this. So in the end, sum this all up, I get s squared over s squared plus 4 times 2 over s squared. These s squareds will cancel, so the Laplace transform for the sine of 2t is going to be 2 over s squared plus 4. And again, if there was a 2, if there was, say, a 3 here instead of a 2, or a 5 here instead, you can see how the answer might change based off of these two numbers. Okay, so remember that the Laplace transform is a linear transform because it's an integral, and all integrals are linear transforms, is that they have the constant multiple rule and the sum and difference rule. So if we were going to do the Laplace transform of, say, two functions added together with, say, constant multiples, so maybe something like this. So not just the Laplace transform of f of t or g of t, but alpha times f of t plus beta times g of t. You could also do minus here as well. Then what we can do here is really the Laplace transform of f of t and pull alpha out, plus the Laplace transform of g of t and pull beta out. So if you think about it, the Laplace transform of alpha f of t plus beta g of t is going to be alpha times the Laplace transform of f of t plus beta times the Laplace transform of g of t. So we would get something that looks like this. So if we know what the Laplace transform of 1 is, and we know what the Laplace transform of t is, we should be able to do the Laplace transform of 1 plus 5t, in that it would be the Laplace transform of 1, which is 1 over s, plus 5 times the Laplace transform of t, so that would be 5 over s squared. We could use that also to do something like this. So this should be 4 times the Laplace transform of e to the negative 3t minus 10 times the Laplace transform of sine of 2t. And since we just did the Laplace transform of each one of those, we would have 4 over s plus 3 minus 10 times 2 over s squared plus 4. So that would give us 4 over s plus 3 minus 20 over s squared plus 4. If you really wanted to go one step further, we could put this all over one fraction. S plus 3, s squared plus 4 being the common denominator. This isn't really necessary, but we could. This would be 4 times s squared plus 4 minus 20 times s plus 3. Multiply, calculate terms, and you get your answer. I mean, this is good enough for now, but the idea is if we know how to do Laplace transform with just a couple of different functions, we can combine them and find the Laplace transform of their linear combinations as well. So here are some of the basic functions that we can take the Laplace transform of. And we've done most of these already. The only one we haven't really looked at is cosine, but it works a lot like the sine does, so I'm just going to jump straight to the formula. So if you look at these, if we know the pattern to these Laplace transforms, we actually don't have to do all that integration. We should just be able to use these formulas to help do the Laplace transform for these basic functions. So like I said, if I said what's the Laplace transform of t to the 10th, knowing that t to the n is done this way, this should just be 10 factorial over s to the 11th. Or if I want to know what the Laplace transform of cosine of 7t is, well, it should be s over s squared plus 7 squared. 7 being the k here, so that would be s over s squared plus 49. So this makes doing the Laplace transform for these basic functions go a lot faster, which is what we're going to need when we go to use this to solve some of our differential equations. How about the Laplace transform of e to the 7t? I don't know why I keep using 7, but let's just go e to the 7t. Well, using this, we would see it would get 1 over s minus 7. Okay. So you need to get these Laplace transforms down. And really, you need to commit them to memory so that we can use them when we're applying Laplace transforms to solve a differential equation. Also, the next thing we're going to do is something called an inverse Laplace transform, which is taking all this and going in reverse. So we'll have this, and we need to figure out what function did that come from within the Laplace transform. Well, again, if you don't have it memorized one way, it's going to be hard to go back the other way. So these 5 you really need to commit to memory. Now every function is not going to have a Laplace transform, because remember the Laplace transform only exists if the resulting integral that we use to define the Laplace transform converges. But not every one of those integrals is going to converge. Sometimes it's going to diverge. It all has to do with whether or not that limit existed. So there's really two conditions that need to be met in order for a Laplace transform to exist. We need to talk about something called piecewise continuous. So each of the separate pieces of a piecewise function are continuous by themselves. So, if a function is defined in separate pieces, so here's one piece, and here's another piece, and here's another piece, each one of these individual pieces has to be continuous. And the second thing, and this is really the biggest one, is that a function f is of exponential order. Now, of exponential order means, you can read the definition, f is said to be of exponential order c if there exists constants c and m greater than 0 and t greater than 0 such that the absolute value of f of t is less than or equal to m e to the ct for all t greater than t, lowercase capital. Really what it tells me is that if my function, okay, grows slower than this random exponential function m e to the ct, where m and c are just these random constants. So if I can find an exponential function that's going to grow faster than my particular function I'm taking the Laplace transform of, and if you looked at that graphically, exponential functions look like this. And let's say my function is, I don't know, just t. T would just be this line right here, y equals t, let's say. Okay? This function is going to grow faster than this function is. So then we would say y equals t is of exponential order, say c, whatever the exponential c has to be. Look at all the functions we found the Laplace transform of so far. T to a power, so t squared, t cubed, t to the fifth, they're all power functions. So there would be t squared, that would be t cubed. You could always find an exponential function that's going to grow faster than any one of those power functions t to the n. How about sine and cosine? Well, sine and cosine have the wave pattern to them. Of course, an exponential function will grow faster than that, so sine and cosine are good ones to do Laplace transforms of. How about exponential functions themselves? E to the kt. Okay. Well, you could always find one exponential function that's going to grow faster than another exponential function, so that should be fine. Think about some things maybe this won't work for. Okay. What grows faster than an exponential? Well, how about a factorial? T factorial. Factorial function will grow way faster than an exponential function would. Or t to the t, this hybrid function. This will grow faster than an exponential function. So these really won't have Laplace transforms. But the ones we've looked at so far are the most basic ones that you'll see. So if a piecewise continuous function, if f is a piecewise continuous function on the interval from 0 to infinity and has exponential order c, okay, then we'll be able to find the Laplace transform for that particular function. A really handy theorem that we can use when we're doing Laplace transforms for little more complicated ones is this first translation theorem. The first translation theorem says that if a is any real number, then the Laplace transform of e to the at times f of t is equal to capital F of s minus a, where capital F of s is the Laplace transform for just f of t. So this is really helpful if we use that to do maybe one of these two Laplace transforms. So think about this one right here. We know the Laplace transform for t cubed is 3 factorial over s to the fourth. Okay? So what if I wanted to do the Laplace transform for e to the 5t s to the third? Well, if I know this already, and all I'm doing is multiplying t cubed times this exponential, which is really what this is saying, then to find the Laplace transform, I just have to do this, which means I have to plug s minus a into the Laplace transform for f of t. So what's a? A in this case is 5. It's what e is, e to the at, the constant in the exponent. So what it says I should do is I should take this one, which is 3 factorial over s minus 4, but instead of s, I should plug in s minus a instead. So that should be s minus 5 should be plugged in where the s is. And I'll get it now to the 4th power. It sure makes doing this Laplace transform a heck of a lot easier because your only alternative would be to actually do all the integration, which is going to take you quite a bit of time. Integration by parts is going to be needed, but this speeds things up quite a bit. How about this next one, this Laplace transform here? Well, again, if you know the Laplace transform of cosine of 4t, which would be what, s over s squared plus 16, based off of our formulas we just looked at. And all I'm doing is taking that cosine and multiplying it by e to the negative 2t. In this case, a is negative 2. Then every time I see an s here, I should be plugging in s minus a. That's what this is telling me to do. So the Laplace transform of e to the negative 2t cosine of 4t should be s plus 2, because it's s minus negative 2, over s plus 2 squared plus 16. So I have s plus 2 over, this will be s squared plus 4s plus 4 plus 16. So I end up with s plus 2 over s squared plus 4s plus 20. And that would be the Laplace transform for e to the negative 2t cosine 4t. So this first translation theorem really does come in handy to do a lot of these Laplace transforms, especially ones that are a little more involved than just a function or just an exponential, but a product of the exponential times some other function. Now it has to be, if you look at it, it has to be the exponential times f of t. So you have to know how to do this, and if you're multiplying it by the exponential, we can then come up with the answer. The last thing we need to look at is how we would take the Laplace transform of just the derivative of a function. And then also we'll do the second derivative of a function. So if you think about how this would work, it's no different than what we were doing. So it's the limit as, say, b goes to infinity of the integral from 0 to b of e to the negative st f prime of t dt. Okay? And then we're going to try and do integration by parts with this. So if you think about integration by parts, you would say, all right, u equals, well, the only thing we could do is say e to the negative st, and dv would be f prime of t dt. So then du would be negative s e to the negative st, and v would be the integral of f prime, which would just be f. So we would get the limit as b goes to infinity of f of t times e to the negative st minus u times v times du, which would be then plus s e to the negative st times f of t dt from 0 to infinity. And this is from 0 to infinity, or 0 to b, I should say. Well, looking at this one here, this is the Laplace transform for f of t times s. So I could rewrite this as the limit as b goes to infinity of this, which would be f of b over e to the sb, again because it's a negative exponent, minus f of 0 over e to the 0 plus s times the Laplace transform of f of t. Well, as b goes to infinity, this thing's going to go to 0. Why? Because the only way it exists is if f is of exponential order, which means this grows slower than this, so that's why this has to go to 0. This is just going to be f of 0 over 1. So overall, what do I get here? The Laplace transform of f of t, we could write as capital F of s times s minus f of 0. So that's what the Laplace transform of f prime of t would look like. that's going to have some significance as we go to solving differential equations with Laplace transforms. All right, we can do the same thing with the second derivative. So this would be the limit as b goes to infinity of the integral from 0 to b of e to the negative st f double prime of t dt. Again, integration by parts, u equals e to the negative st, dv is going to be f double prime of t, or dt. du is going to be negative se to the negative st dt, and v would be now f prime of t. Okay, the integral of f double prime is f prime. So we would get the limit as b goes to infinity of u times v, so that'll be e to the negative st times f prime of t between 0 and b, minus the integral of v du, so that becomes plus the integral of s e to the negative st f prime of t dt. Remember, this is going from 0 to b, but b is really going to infinity. So again, if you look at this, this is the Laplace transform for f prime. Here I would plug b in for t, and a lot of the same stuff's going to happen here. I get the limit as b goes to infinity of f prime of b over e to the sb minus f prime of 0 over e to the 0 plus s times the Laplace transform of f prime. Well, as b goes to infinity, that's going to go to 0 for all the same reasons. And I'm going to be left with negative f prime of 0 plus s times the Laplace transform of f prime. Well, we just said that was s capital F of s minus f of 0. So if you look at what we would get here, we would get s squared capital F of s minus s f of 0 minus f prime of 0. And there's your Laplace transform for f double prime. Again, this is going to be significant when we use Laplace transforms to solve differential equations.